Good day, sir. Good day, classmates. Today, I'll be sharing my insights and findings about how using ensemble methods improve model performance in the study titled A Novel Ensemble Earthquake Prediction Method, or EEPM, published in 2022. So first, my name is Winsol G. Crisip, a Bachelor of Science in Computer Science, major in Intelligent System, Section 3A. Let me explain what the study is about. The main goal of the researchers was to improve short and midterm earthquake predictions, not the exact time of the earthquake, but the probability that it might happen and the possible magnitude range. This is important because earthquake cause major damage, so even a small improvement in prediction can help with early warnings and preparedness. The dataset came from two sources. First is the parametric data from India and Nepal from 2015 to 2019. This includes the usual earthquake measurements like latitude, longitude, depth, date and time, and magnitude. Second, they collected precursor survey data from people in India, Nepal, and Kenya. These are human-reported signs like temperature changes, pressure, unusual animal behavior, falling leaves, and strange water movement. They get it using a Google form survey. Then they converted all of this into numeric form and combined both datasets into one. The idea is simple. Parameters measures what instruments detect, and precursors capture subtle changes that humans observe. When both are combined, the model gets more information to work with. Now, let's talk about the star of the study, the EEPM ensemble method. This is a boosting style ensemble. Basically, instead of relying on one model only, the researchers trained multiple weak learners one after another. And each new model tried to correct the mistakes of the previous ones. In the end, all their predictions were combined into one strong final prediction. The base models included KNN, SVM, XGBoost, Decision Tree, and Random Forest. Decision Tree and Random Forest were the strongest contributors, while KNN and SVM and XGBoost helped in the later stages to reduce smaller errors. For the experiment, they used Pearson correlation for feature selection, then split the data 70% for training and 30% for testing. They evaluated the models using R squared, adjusted R squared, variance, MSC, and RMC, and accuracy. Now, for the results, which are the highlight of this study. The EEPM ensemble achieved R squared of 0.82 and an accuracy of 87.8%, making it the best performing model. The best single model is the random forest, had an R squared of only 0.82. So the ensemble improved performance by around 5% and so on, depending on the metric. The ensemble also reduced error significantly. Variance dropped from 0.27 to 0.19. MSE dropped from 0.26 to 0.20. RMSE dropped from 0.50 to 0.44. In simple terms, the ensemble became more stable, less overfitted, and more accurate than any individual model. For the visual presentation of finds, figures like correlation heat map of selected features were used to visualize these patterns. Each model produced its own correlation map, and the EEPM heat map showed the most stable and balanced relationship among all features. Next one is the comparison table metrics, which includes R squared, adjusted R squared, variance, MSC, and RMSC. It also includes the bar charts of performance measures, which also show the R squared, the adjusted R squared, and so on. And as you can see in this chart, the EEPM has the highest R squared and adjusted R squared. Next one is a comparative analysis of EEPM versus earlier methods. This table and this figure showed a comparison with earlier ensemble methods from 2019 to 2021. The EEPM model had the highest accuracy among all, which got the 87.8%, and the lowest MSC. The drop showed an upward accuracy trend, proving that the 2022 EEPM is the best among the compared models. For more understanding of the graph, you can pause the video so that you can see and classify what the graph indicates. And lastly is the conclusion. It used a unique data set combining parameters and human precursors. It applied systematic feature selection. And the boosting ensemble clearly reduced error and improved prediction. They also compared EEPM with multiple baselines, which makes the results more convincing. But like any study, there are limitations. Earthquake precursors can be noisy and unreliable. The data set only covers a few countries over 5 years, so we cannot assume it generalizes worldwide. And the raw data is not publicly available, which it can be requested but not accessed freely. For future work, the researchers recommended expanding the dataset, adding more geophysical attributes, exploring deeper boosting, and neural networks. And lastly, collaborating with seismologists for real-world monitoring systems. And last one is the reflection and personal insight. Before I end, I want to share what I personally learned. It says, what did you learn about ensemble methods? So I learned that ensemble methods are really powerful because they combine multiple models to produce a more stable and accurate prediction, especially in complex problems like earthquakes where data is noisy. Ensembles help reduce variance and improve performance significantly. What the researchers did in this study, they use boosting, they use it iteratively to reduce the noise. And next question, would you recommend ensembles for similar research problems? Why or why not? My answer is yes. I would recommend ensembles for similar research problems because they give more reliable outputs compared to single models. Like what this study or research shows, the EEPM shows much greater performance than the random forest, which is an individual model. Though they do require more computation and tuning, but it's for the best. And that's all for my presentation. Thank you for listening. These are the references and data. And that's all. Thank you.